Assalamualaikum and hi everyone. So welcome back to my channel. So in this video, we will continue chapter 5, which is part 2, and we are going to focus on subtopic self-induction and also mutual induction. Okay, so let's get started. Alright, so this is the short revision about self-induction. As you know, the definition of the self-induction, it is the production of EMF in a circuit due to the change of current in the circuit itself. So here we have the circuit. So when there is a change of current in this circuit, what happened to this solenoid? So the solenoid will have the self-induction. Okay, so look at here, by running a changing current, so if we want to change the current, so we need to change the value of resistance in the circuit. So what happens when the current is changing means that this area will create a changing in magnetic field, and this will create an induced EMF that fights the change. So let's try to look at this solenoid. So the flow of current, so you can see this is the flow of current I. So this is going upward, downward, and here we're going upward. Same goes to this one and also this one. Alright, so by using your right hand grip rule, so please refer to the video here. So your thumb should be pointing to the left because the direction of the current of the back of the solenoid should be downward and the front of the solenoid should be upward. Okay, so now since the thumb is to the left direction, so this is north and this is the south pole. Okay, so that's why you can see here we have the direction of the magnetic field in this direction. Okay, you can see the blue line showing you the direction of the magnetic field. Okay, so north and south. So what happens when there is a change in current means that the current will be increased or decreased. So when the current is changing, so the magnetic field around the solenoid also changing. Okay, so based on the Len'z law, it will try to oppose the change of the magnetic field around the solenoid. Okay, so we will look at to the next slide. So here we have a solenoid that is connected to the battery. So what happened when the switch S is closed means that the current will start to flow in the solenoid. So initially, the red color of current here is the original flow of current in the solenoid. Okay, so the current produces a magnetic field whose field lines through the solenoid and generate the magnetic flux linkage. So you can see here how to get the direction of the right side of the solenoid is north pole and this is south pole. Okay, so by using your right hand grip rule, okay, this side should be north pole. So make sure you're pointing your thumb to the north pole. So why this side become north pole? So means that when the current flow in this direction, okay, so by using your right hand grip rule, the back side of the solenoid, the direction of the current should be upward. And this is the front side of the solenoid and the current should be downward. Okay, so kita tengok dulu. First, you look at the pole of the battery. So this is positive and this is negative. Okay, so the current will flow in this direction. The current will flow from the positive terminal. Okay, that's why your thumb should be pointing to the right side. Okay, so when your thumb is pointing to the right, so you can get the direction of the other fingers. Okay, yang belakang akan dapat upward, yang depan akan dapat downward. Okay, so automatically this should be north. Okay, so if the resistance of the variable resistor changes, so look at here. So we have the variable resistor here. So when we try to change the resistance in the circuit, the current that flows in the solenoid also change. Okay, so what happened when the current in the solenoid change? Then the magnetic flux linkage in the solenoid also changes. Okay, so as we know that when the resistance in the circuit is increasing, okay, kalau R is increased, means that the amount of current that flow in the circuit should be decreased. Okay, kalau kita decreasekan resistance, the amount of current in the circuit will be increased. Okay, so look at here, what happen if the current of I increases? So what happen when we try to increase the amount of current? By reducing the resistance in the circuit, the current I yang color merah ini, the original current I should be increased. Okay, so what happen when I is increased? So there is a change of current in the circuit. Ingat balik, remember, when there is a change of current flows in the solenoid, therefore, the magnetic flux linkage in the solenoid also change. So, according to the Faraday's law, an EMF has to be induced, ataupun kita panggil sebagai induced EMF in the solenoid itself since the flux linkage changes. Ingat tadi, bila current berubah, so now current is increased, so there is a flux linkage changes. So, bila ada flux linkage changes, according to the Faraday's law, there is an EMF induced in the solenoid. Okay, so you can see here when I is increasing, so according to the Len'z law, the induced EMF here will oppose the changes that has induced it. Okay, so kalau I increase, automatically the direction of the induced current should be opposite direction. Okay, so the direction of the induced current should be opposite direction with the original current I yang color merah tadi. Okay, saya letak sini sebagai I, means that this is direction of the I induced. Okay, so remember, when R is decreased, the current in the circuit, the red color here is increased, meningkat. And the direction of the induced current, okay, is in the opposite direction. So for an increasing current, the direction of the induced field and EMF are opposite to that of the current. Okay, to try to decrease the current, it will try to oppose. Okay, tadi kita tambah I kan, we try to increase I. So what happened? The induced EMF would be in opposite direction. Okay, so current yang akan flow like this lah. Dia akan ke sini and moving downward. So in this side. Okay, it should be opposite direction. Okay, so you can see here the blue color of the pole. In order to get the direction of the induced current downward, okay, yang belakang downward, yang depan akan jadi upward. Ini yang depan yang akan jadi upward. So by using your right hand grip rule, your thumb should be pointing to the left side of the solenoid. So you akan dapat the other fingers yang belakang akan pointing downward, yang depan akan pointing upward. Okay, so the direction of the induced EMF in this direction. Boleh? Okay, sebaliknya kalau current I decrease, okay, we try to increase R, resistance tadi increase, so I, the red color here, okay, the amount of current I will be decreased. And what happen if the current is decreasing, the direction of the induced field and the direction of EMF are in the same direction. Kenapa in the same direction? Because it try to increase the current. Sebab they try to oppose the change of the current. Okay, current tadi decrease, right? So sekarang the direction of the induced EMF in this direction. So means that the direction of the induced current should be in the same direction as the original current. So you can see here, the red color here is the direction of the original current, and the blue one here is the direction of the induced EMF. Sorry, induced current, I. Okay, so therefore, the direction of the induced EMF here is in the same direction of the current I. So you can see here, if the current is decreasing, the direction of the induced field and EMF are in the same direction as the current to try to increase the current. Okay, so kalau kita cuba untuk kurangkan current, induced current akan cuba untuk tambah lah. So you can see that the direction of induced current should be in the same direction as the original current. Boleh? Okay, so this is the definition of the self-inductance. I'm sure that you have learned in your class. So the definition of self-inductance, L, is the ratio of the self-induced EMF in the solenoid to the rate change of current in the solenoid. Okay, the IDT is stand for the rate change of current in the solenoid. Okay. And you can hear the self-inductance of a solenoid. So it's given by N phi over R, where this is the symbol of the magnetic flux passing through each turn of the solenoid, and it's equal to BA cos theta. So when we try to rearrange the equation, L can be written as mu naught N squared A over L. Okay, so now let's proceed to the mutual induction. So it's different with the self-induction, where self-induction just involve one solenoid or one coil, but in the mutual induction, okay, there are two coils involved in this experiment. Okay, so look at here for coil 1. Okay, so coil 1 is connected with a source of voltage. So let's say this is a battery, for example. So this is positive terminal and this is negative terminal. So when the current flow in coil 1, you can see the flow of current here. Okay, so this is coil 1. So means that the current will flow in this direction. Okay, so means that this is the front of this solenoid, where the direction of current is upward and then moving downward, and this is also upward direction. Okay, so depan upward, belakang downward. Okay, kita lukis. Kenapa saya lukis the direction of current in coil 1? Because I want to determine north pole and the south pole of the solenoid. So by using your right hand grip rule, so the direction of current that flow at the back side of the solenoid is downward, belakang downward, depan upward, means that your thumb should be pointing to the left side of the coil 1. Okay, so means here is north and here is south pole. Okay, so betul lah. So based on this diagram, you can see that, okay, the magnetic field lines, okay, will be come out from north pole dan dia akan masuk ke south pole. Same goes to this one. It's moving downward, north to south. Okay, so let's look at the explanation. We consider two circular closed pack coils that located near to each other. Okay, and a current I1 will flow in coil 1. Yes, and the current is produced by the battery in the external circuit. Okay, so the current I1 produce a magnetic field lines inside it. You can see B, okay, the green color here is the magnetic field lines inside coil 1, and these field lines also pass through coil 2 here. Okay, so what happen if current I1 changes with time? Sama ada kita cuba untuk increase ataupun kita cuba untuk decreasekan current dalam coil 1. If the current I1 changes with time, the magnetic flux through coil 1 and 2 also change with time simultaneously. Remember, bila ada perubahan current dalam coil 1, akan ada perubahan magnetic flux di dalam coil 1 dan juga coil 2 tadi. Okay, you can see when there is a change of current in coil 1, so there is also change of the magnetic field strength, okay, inside coil 1 and also coil 2, and at the same time there is also change of the magnetic flux through coil 1 and coil 2. Okay, so due to the change of magnetic flux through coil 2, an EMF is induced in coil 2. Okay, if here we put a galvanometer in coil 2, so here let's say we try to connect the galvanometer in coil 2, you can see there is a deflection of galvanometer in coil 2 because there is an induced current flows in coil 2. So in other words, a change of current in one coil ni merujuk kepada coil 1 lah. A change of current in one coil will lead to the production of an induced EMF in a second coil. So when there is a change of current in coil 1, means that there is an induced EMF produced in coil 2. Okay, so this process is known as mutual induction, where the definition of mutual induction is the process of producing an induced EMF in one coil. So this is referred to coil 2 tadi, due to the change of current in coil 1, in another coil to coil 1 lah. Okay, at the same time, the self-induction also occurs in coil 1. Dalam masa yang sama, so look at here, coil 1, we have a battery here, right? So when there is a change of I1, either increasing or decreasing, so means that coil 1 will undergo the self-induction at the same time. Okay, since the magnetic flux through it changes. Okay, so dalam kes ni, bila perubahan current dalam coil 1, so apa yang berlaku dekat coil 1, there is a change of the magnetic flux through coil 1 and also coil 2. But untuk coil 1, since there is a source of voltage here in coil 1, so coil 1 akan mengalami self-induction. So for coil 2, it will undergo mutual induction. So there is an induced EMF produced in coil 2. Okay, so this is the equation of the mutual inductance. Okay, where mutual inductance M is the ratio of induced EMF in a coil, which is coil 2 tadi, to the rate of change of current in another coil. Okay, the rate change of current in another coil refer to coil 1. Okay, so yeah, so this is the equation. Mutual inductance also equal to, so mutual inductance is equal to the number of turns in coil 2 times the magnetic flux in coil 2 over I1. Okay, so I1 ni, sebab tadilah merujuk kepada kes ini, pada siapa yang ada current? I1 lah, sebab I1 yang ada battery tadi. Okay, so yes, look at here. This is another equation of the mutual inductance. So Sm is equal to N2 times the magnetic flux phi. Phi2 is stand for the magnetic flux, okay, over I1. Okay, where magnetic flux here can be written as here. Okay, mu naught N1 I1 A over L. Okay, dekat sini dia mesti I1 lah, sebab since there is a change of magnetic flux in coil 2 due to current that flow in coil 1, I1 lah. So by rearrange this equation, okay, the mutual inductance also equal to mu naught N1 N2 A over L. Okay, so let's try some examples. So let's start with example number 1. So for question number 1, we have an induced EMF of 5.0 volt. So let's write induced EMF is equal to 5.0 volt is developed across a coil when the current flowing through that coil is changing at a rate of 25 ampere per second. So 25 ampere per second here is actually the rate change of current through the coil. Okay, so let's write di over dt is 25 ampere per second. Okay, it's not 25 ampere, it's 25 ampere per second. Okay, so determine the self-inductance of the coil. So let's try to use equation of the self-inductance, which is L is equal to negative induced EMF, okay, over the rate change of current. Okay, so we can just straightly substitute the equation and it's equal to negative 5 over 25. Therefore, the self-inductance is equal to 0.2 Henry. Okay, so the unit is Henry. Okay, for example number 2, suppose you wish to make a solenoid whose self-inductance is 1.4 millihenry. So L is given as 1.4 millihenry. Okay, so the inductor is to have a cross-sectional area of 1.2 exponent negative 3 meter squared. Okay, so the area of the inductor is 1.2 exponent negative 3 meter squared. Okay, and given that the length of the conductor is 0.052 meter. Okay, so how many turns of wire needed? So we want to find the number of turns. So let's try to recall. Okay, L, okay, the self-inductance is equal to the equation of self-inductance. We know that N times V over I. Okay, where, okay, remember, where the flux is equal to BA cos theta, right? Okay, and we can write phi is equal to, so this is equal to 1, okay, mu naught N I over L times A. So L is equal to N times mu naught N I over L times A. Okay, so rearrange the equation. Okay, remember we have another equation of self-inductance. Okay, mu naught N squared A over L. Okay, so kalau you dah hafal dah formula ni, you can just straightly use sajalah. Okay, we'll substitute all the equations. So we want to find N. Okay, so when N is equal to square root, okay, capital L self-inductance times L over mu naught A, okay, where it's equal to, so let's substitute all the values, 1.4 exponent negative 3 and 0.052 over, so this is 4 pi exponent negative 7 times 1.2 times exponent negative 3. Therefore, the number of turns is equal to, okay, 219 turns. Boleh? Okay, now, so let's proceed to question number 3. So we have 500 turns of solenoid. So let's write N is equal to 500. Okay, and the length is 100 millimeter. Okay, and the diameter is given as 3 centimeter. So since the diameter is 3 centimeter, means that the radius is 1.5 centimeter. Okay, calculate the self-inductance of the solenoid. So given that the mu naught is equal to 4 pi exponent negative 7 Henry per meter. Okay, so we want to calculate the self-inductance. Okay, so this is very easy. We can just apply and use the formula where L is equal to mu naught N squared A over L. Okay, but we need to find first what is the area, the cross-sectional area of the solenoid. Okay, which is pi r squared. Okay, so we just substitute r. So remember, don't be confused or careless because the question gives us the diameter, but we need to use the radius. So bahagi dua lah. Okay, squared and A is equal to 7.0686 exponent negative 4 meters squared. So this is the area. Okay, so mu naught 4 pi exponent negative 7. Okay, 500 squared. So 7.0686 exponent negative 4. Okay, over 100 times 10 power of negative 3. Okay, so L is equal to 2.22 times 10 power of negative 3 Henry. Okay, so this is the answer. Alright, okay, so second, we want to find the current flows in the solenoid. Okay, if the energy stored in the solenoid is 4 millijoule. Okay, so for energy, the equation of the energy, U is equal to half Li squared, where L is the self-inductance and I is the current flows in the solenoid. So given that U is equal to 4 millijoule, okay, so therefore we can find I, so where I is equal to 2U over L. So don't forget to take the square root. Okay, so U is equal to 4 exponent negative 3, and the self-inductance that we got just now is 2.22. So 2.22 exponent negative 3. So take the square root, and finally current flows in the solenoid is equal to 1.9 ampere. Okay, unit jangan lupa. Boleh? Alright, good. Okay, so for question number 4, we have a 400 turns of solenoid. So let's write N is equal to 400, has a cross-sectional area. So the area is given 1.81 exponent negative 3 meter squared, and the length is 20 centimeter. Okay, so the solenoid carrying a current of 4 ampere. So I is equal to 4 ampere. Okay, so let's take out all the information given by the question and then try to solve the problems. Okay, so the first one, we want to calculate the inductance of the solenoid. Means that we want to calculate the self-inductance of the solenoid. L is equal to negative EMF, the induced EMF, over the I over dt. Okay, look at here. If we use this equation in order to calculate the self-inductance of the solenoid, tak boleh. Okay, we cannot solve because we don't have the rate change of current. Okay, kita tak ada berapa masa dt dia. So you cannot use this equation. Okay, so let's try another one where L is equal to mu naught n squared A over L. Okay, so by using this equation, remember for self-inductance, we have two equations, right? But we can use the second one. Since we have, so mu naught is 4 pi exponent negative 7. The number of turns is given 400. And then the area is also given. Okay. And the length is, the length is 20 centimeter. 20 centimeter. Okay. So press your calculator. So L is equal to 1.82 exponent negative 3. Okay, and the unit is Henry. Don't forget the unit. Okay. So number 2, calculate the energy stored in the solenoid. So we want to calculate the energy stored in the solenoid. Okay, where U is equal to half Li squared, half where L is 1.82 exponent negative 3, and I is current flow in the solenoid is 4 ampere. Don't forget I squared. Okay, so U is equal to, berapa dapat tu? U is equal to 1.5 exponent negative 2 joule. Okay, so this is the answer. Alright, so number 3. So let's proceed to question number 3. So I just write here. Calculate the induced EMF in the solenoid if the current drops uniformly to 0. Okay, the current drops uniformly. So that means initial current tadi 4 ampere. So now the final current will be equal to 0. Since the question states that the current drops uniformly to 0 ampere in 55 millisecond. Okay, means that di over dt is equal to 0 minus 4 over 55 millisecond. Okay, 55 millisecond. Okay, so now let's proceed. We want to calculate the induced EMF, right? So the equation, so let's write the equation where induced EMF is equal to negative L di over dt. Okay, So please remember, so this is the equation. Okay, so now we can just substitute all the values. Okay, so where induced L is equal to, okay, just now we got 1.82. Okay, 1.82 exponent negative 3 di dt 0 minus 4 over 55 millisecond. Okay, therefore induced EMF is equal to 0.13 volt. Okay, alright, so finish example number 4. So let's continue with example number 5. Okay, example number 5 is about mutual induction. Okay, so we have a primary coil 80 centimeter length. So let's write the length of the primary coil is 80 centimeter. Okay, and the diameter of the coil, okay, is given as 12 centimeter, but I just write the radius. In order to find the area, we need the radius, right? So the radius of the primary coil should be half of its diameter, so it's 6 centimeter. Okay, negative 2 and the number of turns for the primary coil is 6,000 turns. Okay, so the current flows in the primary coil, so it's given at rate of 3.0 ampere per second. So it's give you dI P over dt. Ataupun saya nak tuliskan ataupun saya nak tulis di dt P for the primary coil is given as 3.0 ampere per second. Okay, so what else? Calculate the mutual inductance and induced EMF produced in the secondary coil, where the number of turns of the secondary coil is given as 70 turns. So for the secondary coil, let's write the information. It's N is equal to 70 turns. Okay? Yeah. So let's proceed. Calculate the mutual inductance in coil 2, secondary coil. So let's write the equation where M is equal to, okay, we can write M is equal to mu naught NP NS A over L. Okay, so yeah, we can just substitute, right? But we need to find first what is the area. So the area is equal to pi r squared. Okay, so you can just substitute. Okay, pi 6 exponent negative 2 and the area is 0.113 meter squared. Okay, so therefore the mutual inductance is 4 pi exponent negative 7. The number of turns for the primary coil is 6,000, secondary is 70, and the area is 0.113. Okay, so the length of the coil is 80. Okay guys, in this case, so we have a primary coil here, okay, where the number of turns, let's say the number of turns is 6,000, right? So this is the primary coil. Okay, so NP, and at the same time we have the secondary coil. Okay, sorry, and at the same time we have the secondary coil, okay, where the number of turns of the secondary coil is equal to 70. Okay, so the length L is still the same length, since the length of the primary coil is equal to 80 centimeter. Okay, so let's substitute and let's try to calculate the mutual inductance, and it's equal to 7.46 exponent negative 3 Henry. Okay, so finish example number 5. So let's proceed to example number 6. Okay, example number 6, a current of 3 ampere flows in coil C and it is produced a magnetic flux of 0.75 Weber in it. Okay, so in this case, we have two coil. Okay, so this is coil 1. Okay, so let's say this is coil 1. Okay, let's say we have R. Okay, and another one, so we're gonna have second coil. Okay, coil 1 and coil 2. So the current of coil C, in this case we use C and D, so let's write C and D. Okay, so let's take out all the information. So the question states that the current that flow in coil C is given as 3.0 ampere. Okay, and the magnetic flux that produced in coil C, okay, is equal to 0.75 Weber. So when coil D is moved near to coil C, a flux of 0.25 Weber is produced in coil D. Okay, if coil C has 1000 turns and coil D has 5000 turns, this one is 1000. Okay, calculate the self-inductance of coil C and the energy stored in C before D is moved near to it. Okay, so as we know, coil C will undergo self-induction. Okay, since the source of voltage is connected in coil C. Alright, so when the amount of current in coil C is increased or decreased, so coil C will undergo the self-induction. So let's calculate first the self-inductance of coil C. Okay, so A, where L is equal to NC, okay, times the magnetic flux in C and also the current flow in C. Okay, so substitute all the values. All right, and it's equal to 250 Henry. Okay, and we also want to find the energy stored in C before D is moved near to C. Okay, so U equal to half Li squared. Okay, so half L is 250, I is 3 squared. Okay, and the answer is 1125 joule. So when coil D move near to C, so there is a process that we call as mutual induction. So now we want to calculate the mutual inductance of the coils. Okay, so B, we can write M, where M is equal to the number of turns, so M is equal to the number of turns in D, okay, times the magnetic flux in D over the current in C. Okay, so it's equal to 5000 times the magnetic flux is 0.25, right, over IC is 3, so it's equal to 416.7 Henry. Okay, so okay, for question C, if the current in C decreasing uniformly, that's mean di over dt in C, okay, from 0 to 3 over 0.25, calculate the induced EMF in coil D. So we want to find the induced EMF in coil D. As we know, induced EMF is equal to negative M times di dt. Okay, so we can just substitute negative 416.7 times 0 minus 3 over 0.25 second. Okay, therefore the induced EMF is equal to 5000.4. Okay, so we finish example number 6. So means that we reached the end of the video. Okay, so that's all. Don't forget to share, like and subscribe. Assalamualaikum dan selamat sejahtera.